Okay, well, we've talked about linear hashing in another video. That was linear hashing in general. And now I want to have a quick look at PostgreSQL's implementation of linear hashing, which is a little bit unusual. But anyway, how do you get a linear hashed file in Postgres? Well, you create an index on the file. And this is the kind of index you want to create, and essentially that creates a hash table or a hashed file. Alright, the implementation lives in that directory. There's a number of .c files that contain interesting things. So for example, there's a whole bunch of different hash functions that are specialized for different data types. There's the function that handles insertion, including overflows. There's a function or a source file that handles various utilities and the splitting process. And of course, there's an iterator that allows us to scan through hash files if needed. There's a nice README in this directory which contains an extensive description of how everything works. And the linear hashing that they use in Postgres is based on this work from 1991. Alright, just a reminder, here's Postgres' generic hash function. And you can see that it takes in a byte array, which is effectively what that means. That's how long the array is, and it produces a 32-bit integer result. Right, so the details of that. So this is a cut down version of it. The details are in that file there. So what a hash any gives you is 32-bit quantity. Actually packaged as a datum. Alright, so there are hash any, or a faster version of hash any called hash uint32 is invoked from a bunch of type specific functions. So here's the function for hashing 4-byte integer values. And as I mentioned, the hash value ends up being wrapped as a datum. Alright, well, part of any linear hashing is, of course, the fact that we have a split pointer and part of the file up to the split pointer is indexed by an extra bit of hash key as opposed to the middle bit of the file, which is indexed using one less bit. Now, Postgres doesn't quite have a notion of split pointer, but what it does have, it has these high masks and low masks. So the high mask is going to set a certain number of bits, and the low mask will set less bits. And so we've got a max bucket values, that's fine, and the hash key itself. So that's what's fed in. We compute a bucket number based on the hash key. If that happens to exceed the max bucket value, then we need to convert it to something that does fit in the file, the page indices of the file. So this is kind of doing a little bit the converse of what we did in regular linear hashing. This basically takes d+1 bits and performs does a mask to give you d+1 bits of the hash key. If it turns out that that value is larger than the size of the file, then it uses one less bit to work out the actual bucket address. So rather than computing d bits and then maybe upping it to d+1 bits if we're less than a split pointer, it does it that way. Alright, now one unusual thing about Postgres is the way it organises the file. The way we talked about it earlier is that we have a data file and we have an overflow page file. Well, Postgres actually uses a single file which contains a header page, also called the metadata page. It has the regular data pages and it has the overflow pages. The header page is always the first page, and the main and overflow pages are actually intermingled in the file. Got a diagram coming up that will show that. But the data pages are inserted into the file in groups, whose size is always a power of 2. In between these groups we have overflow pages, and we can have as many overflow pages as are required between each group of data pages. So how do we work out where all these groups are? Well, the header page contains a bunch of group pointers, and each group pointer indicates an offset to the start of a group of data pages of size 2 to the n. If overflow pages become empty, then they can be added to a free list of overflow pages. So we don't actually, have a overflow file that's got a bunch of empty pages in it. We may have empty overflow pages in the data file, but we can reuse them. Just to be confusing, Postgres calls these group pointers split pointers. Now that's totally different sense to what we were using in talking about linear hashing in general. Right, so here's what the file looks like. So this is the header page, or at least part of the header page, and here's the main file consisting of pages. The first page is the header page itself, so this is actually part of this. Then we have 2 data pages, some overflow pages, 2 more data pages, 1 overflow page, 4 more data pages, overflow pages, and so on. So the size of these groups, the number of pages that they allocate, is actually determined by the current size of the file. So as the file gets bigger, the number of pages in a group tends to get bigger as well. But like I said, it's always a power of 2. Now, of course, we've got the physical index of these pages, page 0, 1, 2, 3, 4. The data pages, notionally, have an effective index. So this is the first data page, 0. So this is bucket 0, if you like. Bucket 1, bucket 2, bucket 3, buckets 4, 5, 6, 7, and 8. Right, and they happen to be in this 15 total pages. Right, so that's slightly unusual file structure, but it saves having an extra file, I guess. And clearly, under that file structure, we need a way of taking a bucket address and mapping it to a physical address. So we might say, all right, we need to have a look at bucket 2 because the hash value is 2. Well, that corresponds to physical page number 5. So what we need to do is convert this 2 into the actual address. And here's roughly the way we do it. So the header page has an array of pointers to group pages. So this is effectively the group page pointers. First thing we do, we work out which chunk of pages, data pages that we're talking about. So like I said, that's the first chunk of data pages, the second chunk, the third chunk, and so on. So we need to work out which of those we're talking about, and this is the formula for doing that. Once we've got a chunk number, we can then look at the splits array and work out the base offset of the group that the page, that bucket B, is a part of. Of course, that's not the whole deal. We can work out, say, that bucket 1 is located somewhere. Sorry, it's not. Bucket 2 is located somewhere in this group. And the way we'd work that out, we take the number 2, we'd run it through that thing to work out which chunk. It would say chunk number 1, and that gives us the a pointer to the first data page in the group. We then need to work out whether it's this one or this one. So that's the offset within the group. And so that's worked out there. And then we compute the actual physical page number by going to the base of the group and adding the offset. And that'll give us a physical page number. Part of the deal with working this thing out is we need to work out log 2. You don't want to do it using the mathematical library log function. That's way too slow. So what we actually do is we start from 1 and we double it and double it and double it until it's larger than the value whose log we're looking for. So the number of doubles that we have to do is equal to the log. Yeah. And that pretty much covers hashing in Postgres. If you want to go and have a look, I've given you the directory where all the files are, and so you can go and scan through the thousands of lines of code to see exactly how things are implemented. If you do that, you're going to discover that a lot of the code is related to handling concurrency. So how do we deal with the fact that and especially it becomes problematic when we're doing page splitting, because you've got a page that is sort of in flux, if you like, and there may be other transactions that are trying to insert things into that page. So there's a lot of code to deal with handling that kind of stuff. But it's an interesting way of doing linear hashing.